Hello and welcome to our webinar today on optimization of pipeline integrity management activities. This is the first in a series of technical and informative webinars brought to you by Penspen. My name is Annie Ross and I am Penspen's Global Marketing and Communications Manager, and I will be your host for today's webinar. Today's presenter, Jonathan Doyle, Senior Integrity Engineer at Penspen. Jonathan has over 13 years experience in engineering consultancy, primarily focused on subsea and pipeline integrity management. Before I hand over to our presenter, I'd just like to quickly run through some housekeeping for today's webinar. If you have a question at any time during the webinar, please submit it through the Q&A functionality. You will see the icon on the presentation slide with the two speech bubbles and the question mark. Click on that and it will take you to the Q&A functionality. You will also be muted throughout the webinar, and also the webinar will be recorded and shared with you shortly afterwards. Now I'd like to hand over to Jonathan Doyle, who will be our presenter today.
Thanks, Annie, and good afternoon, everyone. Thanks for your time this afternoon. As Annie has mentioned, this is the first in a series of presentations, so there'll be a few topics that I'll touch on quite lightly, but will be expanded on later in the series by some of my colleagues. So in terms of what we plan to discuss today, overall the aim is to provide some insight into how integrity management activities can be optimized so that we can continue to safely manage our assets while also controlling expenditure. So our brief agenda then is to firstly introduce the concept of integrity management and then move on to the topic of risk and risk management within that context. Discuss how risk assessment can be used to identify and optimize required inspection integrity activities, and to look at how we can potentially maximize the value of the data and the information that we gather from these activities during the pipeline life cycle. So without further ado, I think the best place to start really is with a definition, and the dictionary definition of asset integrity management is a system used by owners and operators to ensure the safety of an asset from its conception to its retirement. So then moving on logically from that, pipeline integrity management is a system used by owners and operators to ensure the safety of a pipeline from conception to retirement. So why might we want to manage integrity? The first thing really primarily is to prevent harm to people, both those that are in our employment and to the general public. We also need to protect the environment. We work in hazardous industries. These pipelines convey some pretty serious stuff, hydrocarbons and other chemicals, and often they're routed through ecologically sensitive areas, so we need to ensure safety to maintain the environment. We also need to comply with all relevant legislation. In the UK, that falls underneath the kind of umbrella act of the Health and Safety at Work Act. And then there are specific pipeline regulations that arise from that act for various different assets and industries. So for pipelines, we're talking about things like pipeline safety regulations, pressure safety regulations, safety case, COMA, onshore, and various others. We also want to maintain our corporate reputation, protect ourselves as a business from potential failures, and convey a positive image in the industry and in the media as well. And then finally, of course, we need to make money in order to be a viable business, and managing integrity helps us maintain productivity, potentially increase productivity, and avoid unnecessary losses and costs arising from shutdowns. So that final topic there about maximising revenue and profits also feeds into the sort of topic of the discussion of optimisation of integrity management activities. So if we can optimise what we're doing, we can manage our budgets and control our costs. And this is particularly important during periods of low commodity prices. But there's also evidence that historically, safety incidents have increased in the years following downturns in oil price and other commodity prices, where activities might be deferred or postponed. So it's important that we understand our risks where those high risks are and ensure that what activities we do undertake are the right ones to sort of maximise safety while controlling cost. So moving on. Just a few examples quickly of what happens when we don't manage integrity. I'm not picking on anyone in particular. These are just some that fitted in quite neatly with the topic at hand. In 2008, on Varanus Island in Australia, there was a significant explosion and fire. Thankfully, no injuries, but it affected 30% of Western Australia's gas supply for up to 6 months. The cost to the state economy alone was $3 billion. The gas that was generated from the facility supplied the state's electricity as well, so it wiped out domestic gas and electricity, as well as agriculture and other major industries. The investigation found that the failure occurred at the sort of beach crossing section of the pipeline as it came from offshore to onshore. This is a kind of common hotspot for corrosion, and it should have been managed properly and ensured that the risk was identified and suitable safeguards were put in place. Unfortunately, that wasn't the case. It was found that that particular section hadn't been inspected for almost 16 years. And that obviously shows a shortfall in the risk assessment and integrity management process, and a cost and risk that could have been easily avoided. Another example, in 2010, in San Bruno, California, unfortunately, this incident did result in 8 fatalities, as well as the destruction of 35 houses. I believe some other houses were pulled down as well several months after the event. It was initially mistaken for an earthquake or potentially even a plane crash, as the location was only several miles from the nearest airport. This confusion actually led to the fire being more severe than it needed to be, because no one realised that they needed to shut off the gas supply until several hours after the event. Again, there was some significant knock-on effects here. The operator was challenged by the regulator and couldn't put forward any rational argument as to how they demonstrate the integrity of their pipelines, so they were forced to operate with their entire network at a derated pressure, which had a huge knock-on to revenue. It had a massive knock-on on their share price as well, wiped off $1.5 billion. And then the investigations found that the pipeline contained defective welds. It was a 1950s vintage pipeline, and the pressure had been continually increased over time to meet increasing demands, but at no point had it actually been given a sufficient integrity assessment or subject to sufficient inspection to determine that it was safe to operate at those higher pressures. And unfortunately, this is what it led to. So thankfully, as an industry, we do learn from our mistakes quite quickly, and they quite often then become legislation. The pipeline safety regulations in the UK themselves are the result of a shake-up in the regulatory regime following Piper Alpha, which is the UK's most significant oil and gas incident to date. And what that's pushed forward was a move away from a prescriptive box-ticking culture, where things were done purely to tick the box, to a more goal-setting approach, and the adoption of risk-based and risk-informed strategies for integrity management. Unfortunately, incidents do still happen. These are 2 incidents from this year. The first one in July in Mont Belvieu, Texas, where there was an explosion and fire at a natural gas storage facility. It appears that a contractor working over a pipeline struck the underground pipeline, causing an explosion and fire. Thankfully, no one was injured in that incident. And then in August, just a month later, in Corpus Christi, Texas, there was another fire and explosion, this time on a submarine pipeline, where a dredging vessel hit a propane line. 6 people were hospitalized in that incident, and at the time, the news was reporting that there were 4 people unaccounted for. So another serious and significant event that could potentially have been avoided, but the investigations for those 2 incidents are still ongoing. So moving on then, what does integrity management actually look like? The figure there on the right-hand side is taken from DNV RPF 116, which is the recommended practice for integrity management of submarine pipelines. And if you're not familiar with it, hopefully you are familiar with the Plan, Do, Check, Act cycle, common in ISO standards. And essentially the integrity management process follows the same path. It's a continuous and iterative process, and it's common to a number of sort of asset management codes and standards. So if we move on, this is taken from ISO 55001, which is for asset management systems. And again, we can see there's a similarity here with what was presented in the integrity management standard for submarine pipelines. There's many of the same steps and many of the same points. One thing to pick out on this diagram is that it quite clearly highlights the importance of leadership from the top of an organization and how that influences the mindset and mentality of a business and how it manages safety and integrity across its entire asset base. So on that basis, then, the goal really of integrity management is to understand and control our risks. On the right-hand side there, we've got a diagram, the Swiss cheese model, which hopefully people are familiar with. And the idea there is that you can reduce your risks by adding barriers. We want to put as many controls in place as we can, robust controls, to ensure that an incident doesn't escalate to potentially significant failure. So within the UK, and I'm sure other legislation, we talk about ALARP and reducing risks to a level that is as low as reasonably practicable. Now that has a sort of legal definition. It's a narrower term than practical. So we're not looking at something that is possible. We're looking at something that has a benefit that is both feasible and worthwhile. So there's an element there of computation of the benefit or the magnitude of risk reduction versus the cost, whether that's time, money or effort to implement that mitigation. So where something is grossly disproportionate, then it's not. It can be argued that it's not required. An integrity management system then is a systematic approach to demonstrating how those risks are controlled and how your integrity is maintained. And an integrity management plan, some codes and standards call it an IMS or a PIMS, that outlines your approach to risk management in terms of your organisation, resources, procedures, and the mitigations that you have in place to control your risks. There'll be further discussion on the topic of PIMS later on in the series of Insight webinars. So on that basis, then, risk is fundamental to integrity management. And just in terms of a definition of risk, what we're talking about really is the chance of loss, and it is the function then of probability of an event and the consequence of that event manifesting. Risk analysis is the identification of hazards contributing to risk, and then the identification of the failure consequences and determination of the likelihood of that failure occurring. And then risk management overall then is the process of selection and implementation of risk reduction measures in support of ongoing integrity management. So we can consider risk management as 3 key steps of estimating, evaluating, and managing risk. Next slide, please. So this might be a term that you've heard before, risk-based inspection, or RBI. RBI is the process of applying those risk analysis and risk management techniques specifically to determining the type and frequency of inspections that are required to control risk at an acceptable level. Within the UK legislation, PSR Regulation 13 states that the operator shall ensure a pipeline is maintained in an efficient state, in efficient working order, and in good repair. And within that definition, the word maintenance there includes the inspection. So what we can see then is within the legislation and within the code guidance, risk-based approach to integrity management and to assigning inspection activities is acceptable and is industry accepted. It is increasingly common, but at this stage it isn't universal. Some inspection activities are still assigned based on a sort of preventative maintenance approach rather than a risk-based approach, and that does mean that there is still scope for some optimization in some of the activities that operators are undertaking. So another question then is, how exactly does inspection control risk if we're going to use that as an effective mitigation within our integrity management system? Essentially, inspection is used to monitor the condition of an asset without inspecting, without looking at our asset. We don't know what the condition is. It's only assumed, and over time, the uncertainty in that condition will increase, which will increase our risk. So, another way of looking at it is what the hazard is like how it manifests. If it's a time-dependent hazard, then inspection will identify the degradation over time, and it will inform our modelling. If a hazard is randomly occurring, if it's not a degradation mechanism, it's a random event, then what inspection allows us to do is identify whether that event has occurred or not, more of a binary approach. One thing to bear in mind, though, is that inspection in and of itself doesn't guarantee integrity. You need to do something with the information that you gather from those activities. But what it does mean is that the frequency of inspection does change the risk and gives us the opportunity potentially to optimize our inspection schedule to maintain our risk at an acceptable level, but potentially reduce our spend. So there are a number of techniques and tools and even various softwares and guidance for performing risk assessments, but there's some key steps that are worth bearing in mind. The first one is that it will always involve identifying the credible hazards. What is it that you're concerned about? What is it that's posing the threat to your asset? The next step then is to define what is a failure, so that you can compare apples with apples, really. So it might be that you're looking at a loss of operation at all, whether that's a blockage or some kind of malfunction, or whether you're looking at a more significant loss of containment where you do actually lose hydrocarbons to the environment and potentially expose personnel to those hydrocarbons. Then you need to determine your consequence of that type of failure. Usually this is health, safety and environmental, as well as economic and reputational. The next step then is to determine the likelihood that failure could occur, and then there's some computation there to determine what the risk is, the product of those two values. And then finally, but important is to define what then is an acceptable risk. You have this output from your process, from your flowchart. You need to make sure that is acceptable, and if it isn't acceptable, then what further mitigations do you need to put in place? So there's industry guidance out there for integrity management, and that includes the identification of hazards. DNV RPF 116 that I've already mentioned has a table of credible hazards for hydrocarbon pipelines. There's similar information in British Standard PD 8010, and then in American code guidance as well, such as ASME B31.8S and API 1160. And then slightly more niche ones, the Energy Institute has also published guidelines for management of subsea infrastructure, and then there's API 17B as well, which covers flexible pipelines. But in general, the approach is similar, and what they identify are key hazards. Typical ones would be things like corrosion, both internal and external, mechanical damage from some kind of third-party interaction, and then other risks such as human error, operational issues, and then other things like fatigue. So risk assessment is an iterative process. You can work through your flowchart and get to the bottom, compare that against what is an acceptable risk, and find that what you have is unacceptable. So you need to look again at what mitigations you can put in place to reduce that risk to an acceptable level, to as low as reasonably practicable. So there's a number of mitigations or controls that can be put in place. Some of these you can say are inherent, they're fixed. Typically these are the design mitigations, so there are plenty of hazards that might manifest that can be ironed out of your design or your system at the design stage by selecting appropriate materials, a sufficient wall thickness, routing your pipeline away from sort of high consequence areas and things like that. These are notionally fixed, but there is some occasionally potential for the introduction of additional physical protection, whether that's mattressing subsea or slabbing onshore pipelines, or in extreme circumstances even maybe rerouting sections of a pipeline. Then there's other kind of in-service mitigations, and I've split these into organisational and operational. The organisational ones are, I guess, what you'd call soft mitigations, so they're more procedural, and these sort of cascade down from management in terms of the sort of strategy or mindset that the business operates with. Training and competency is another key one, ensuring you have competent people who are suitably trained to operate your asset, and then also having emergency response procedures in place. For some pipelines in the UK, this is a legal requirement, and then there's also emergency repair systems that reduce the potential downtime in the event that you do have some kind of failure. The operational mitigations are things like monitoring, online monitoring and control of operating conditions. Chemical inhibition as well is a big one in terms of controlling the risk of internal corrosion, cathodic protection for external corrosion, and then finally inspection as well, and maintenance activities. So there's, as I mentioned before, there's various types of risk assessment, and they do kind of vary in terms of complexity. The most basic form is qualitative, where risk is subjective and can be based on things like rule of thumb or expert judgment. And then moving further along the complexity, we move towards sort of semi-quantitative risk assessment methods that involve some more complex computation, but they're maybe not fully quantitative. And then finally, quantitative risk assessment, where you're calculating your risk based on numerical estimates of probability and consequence. So that's the sort of goal really to reach that level, but typically there isn't as much data available to perform that type of assessment. So typically we sort of fall more within the semi-quantitative risk assessment area, where you use the data that you do have available and then rely on rules of thumb and expert judgment to fill in those gaps in data. Data management is fundamental to integrity management as a whole, and risk assessment as well. Thinking back to the San Bruno incident that I shared earlier, data management was found to be quite a significant contributing factor to the failure, whereby the operator had very poor records, and that contributed to them not fully understanding the risks posed to their pipelines and resulted in a failure. So moving on, once you've performed your risk assessment and you have your risk output, you know where your highest risks are and what mitigations you want to put in place to control those. The next step is to then move on to assigning your inspection intervals. This is where you're looking at the kind of CapEx activities that you want to undertake to maintain the asset condition. There's published guidance available in terms of what is an appropriate inspection interval, and there's recommended practices as well. There's plenty of engineering judgment that can be used there as well, which is perfectly acceptable within the legislation in the UK. There's plenty to be said for experience in terms of knowing the risks and understanding when inspection and other maintenance activities need to be performed. There are cost-benefit approaches that can be performed. These have been developed for various reasons. QRA in particular has seen quite significant development of cost-benefit approaches, and these can be applied in different ways to assign different integrity management activities. But the key really is to try and link as best we can the risk output with the activities we want to perform to ensure that we're optimizing what we're doing on an annual basis. So the Pen risk-based inspection approach, the PERMI model, allows us to have that direct link between the inspection interval that's assigned and the risk that's been output, and that helps us show how risk can be controlled at an acceptable level, specifically for hazards where inspection is firstly possible, and where it can be seen to actively contribute to the control of risk, and also where that inspection then is carried out as recommended or where required. Where inspection is not carried out, we can also use this approach to measure the increase in risk and whether we still remain, within a tolerable level, or whether inspection or some other integrity activity needs to be performed. And where inspection isn't possible, then we can determine what the essentially unmitigated risk is, and if that is unacceptable, then that's where we need to look at other potential controls to reduce that risk to an acceptable level. So where this benefit benefits the operator is it provides a level of rigor that might not be available through more qualitative engineering judgment-based approaches. I've sat through a number of risk assessment workshops in the past where if they can take a number of days and involve a number of experts and personnel, and if those personnel change throughout the workshop, or that workshop takes several days, what you can find is a potential lack of consistency throughout quite a complex risk assessment. This kind of structured approach that we've developed within PenSpan allows us to ensure that things are repeatable and the outputs are more easily justifiable. So in terms of what that process looks like, it's very similar to the flowchart I flagged up earlier. I think the key things really are to segment your pipeline or your system and into the parts that share common hazards or common design or common in terms of location or threat. And then the next difference really is the definition of the hazard failure characteristics, whether we're talking about time-dependent hazard or random hazards. There is some guidance out there that also talks about resident threats, a sort of third category, but typically these are things like manufacturing defects, where if they are going to contribute to a failure, it's typically through some kind of time-based degradation mechanism, such as fatigue. So typically we would class these under as a time-dependent hazard rather than a third category. Moving down the flowchart, again, it's with any risk assessment methodology, you're comparing your probability of failure with the consequence of failure to determine your risk, and then ensuring that remains acceptable, and outputting an inspection interval based on that risk profile. Next slide. So a key part of this process then is determining what is tolerable risk, and that allows us to determine what the probability of failure can be for a fixed consequence and still remaining within that risk tolerability level. So essentially what we're saying then is for a higher probability of failure, we can only tolerate a lower consequence, or conversely, for a low consequence, we can tolerate a higher probability of failure. And then for a high consequence of failure, we can't tolerate the same probability of that failure occurring in order to maintain a consistent level of risk throughout the system. So moving on. Again, there's published guidance on what is acceptable or tolerable probability of failure. On the right-hand side, there is the risk tolerability caret. That's generated from HSE's document, Reducing Risks, Protecting People, or R2P2, and that gives us some orders of magnitude of failure probabilities that are considered to be tolerable, both from an individual point of view and a societal point of view. And then again, on the left-hand side, referring back to DMV RPF 116, there's some more sort of rules of thumb in terms of orders of magnitude of probabilities of failure. And we can use these to inform our kind of our tolerable risk level. So moving on. So the output from our PenSpan RBI model is a typical kind of 5x5 Boston Square matrix. This is typically only because it's familiar to most users. It's consistent with the published guidance in terms of being 5x5. It gives you a clear visual representation of what your risk profile looks like, and you can look at this from an asset level or an individual segment level or a hazard level. And what it shows us essentially is that along the diagonal is where we have our tolerable risk limit, where for higher consequence we can only tolerate low probabilities, and for low consequence events we can tolerate a much higher probability and still be at a tolerable risk level. The PERBI methodology that we've developed is quite flexible, so we can amend the outputs to align with operators' corporate risk matrices, which over time have become slightly more complex or more refined. We've seen 6x6 or 6x8 or alphanumeric risk outputs, and again we can overlay this output to ensure that we are consistent with the corporate risk matrix while still remaining on that total risk limit. Moving on. So briefly, just a quick overview of how the risk assessment process works. For time-dependent hazards, we can consider an estimate of time to failure. There's various models that can be developed for the different hazards that can be considered time-dependent, whether that's corrosion or fatigue or some kind of combination of the two. These can be complex or they can be relatively simple. Essentially, the diagram there shows what we have quite a simple deterministic estimate of remaining life over time, and in reality there are some unknowns, uncertainties, some conservatisms in that estimate. So in reality what we have then is more of a distribution rather than a fixed point in time. So by considering it as a distribution and the consequence in our estimate of that remaining life, we can then consider then a probability of failure rather than a single deterministic point in time. Moving on. So I'm no expert in Bayesian statistics, but essentially what that distribution allows us to do is to present the potential, the probability of failure as a cumulative probability of failure. And if we have a fixed tolerable risk level and a known consequence of that particular failure, then we can determine what the acceptable probability is to maintain risk at that tolerable level. And essentially then that tells us for a fixed consequence how far up that cumulative probability curve we can go before the risk of failure occurring exceeds that tolerable limit. So essentially then, if we have that information available, what we can do then is assign an inspection interval that allows us to go back and confirm the condition of our asset before we reach that point where uncertainty is such that the risk of the pipeline having failed is greater than the tolerable level. Of course, we want to set this inspection interval at a point where that gives us time to act on what we find. And what that information then allows us to do is to go back, accepting that risk assessment and integrity management is an iterative process, and feed back the findings from that inspection into our model and potentially refine the model and whereabouts we are on that failure curve over time. And then that allows us to then determine when the next inspection is due. So moving on to random hazards, essentially there's two steps to this. The first one is that you require some kind of initiating event in order for failure to be credible, and then once that damage has been introduced to your asset, there will be some time to failure, and that then is similar to what we've seen for the time-dependent hazard. So we can combine those two curves, and that gives us a similar kind of cumulative probability curve to what we saw for the time-dependent hazard, slightly modified to account for the fact that there's an initiating event that needs to occur before degradation. So for impact events that result in instantaneous failure, then there's obviously some limitation in terms of how long you have before that initiating event before you need to inspect and identify it. So that's potentially an example of where inspection isn't the best method for controlling your risk, and there's potentially some other alternative mitigations that should be considered. But for those events where damage is introduced and it will degrade over time, then again this process allows us to assign an inspection interval where we can go and confirm asset condition before the probability of the asset failing exceeds the sort of tolerable risk level. In terms of the probability of an incident occurring in the first place, there's various industry failure data available that can be used as a baseline. In the UK, offshore there's Parlock, and more globally there's OGP has a similar sort of failure data set. Onshore in the UK, UCOPA retains failure data for onshore pipelines, and similarly in Europe there's EGIG and Konkawi data sets. So we can use these as our first point of determining what the potential for some kind of impact damage being, and then we can modify this if sufficient company specific data is available, or even, depending on how long an asset has been operated, asset specific data. So for a random hazard, then we can consider the curve to be like a sawtooth. Over time, the uncertainty in the condition of the pipeline increases until we reach our kind of risk tolerability level, at which point we then inspect. And if we find that there's been no damage, then our cumulative failure probability resets to 0 and we start again. If the inspection finds that there has been some kind of damage introduced, then potentially that sawtooth starts to shorten over time, or we can consider it as a time-dependent failure mechanism instead, and apply a different approach to modelling time to failure and determining a suitable inspection frequency. So moving on then, just to summarise the Penspen-Purby approach. Inspection can be used to limit failure probability and control risk. There's various methods for performing risk assessment, and there's various rules of thumb or approaches for determining a suitable inspection interval for a particular pipeline. But the Purby approach allows us to directly link those inspection intervals to the risks assessed, and gives us the opportunity then to optimize our inspection schedule based on the risk assessment output. So the key then obviously is to ensure that inspections are scheduled such that we don't exceed the acceptable failure probability to maintain risk at a tolerable level, and then after each inspection the uncertainty in our asset condition is reset, and we can revise our predictions in terms of a time-dependent degradation model, or for random hazards we can reset our cumulative probability of failure back to 0. In terms of the benefit of this, we've recently carried out a project for a UK offshore operator who are performing 3 yearly offshore inspection campaigns for all of their assets. What we found when we reassessed their risks using this Penspen approach, that a number of inspections could be pushed out while still retaining a tolerable risk level. And this essentially means that in future their inspection campaigns will be shorter, because there will be fewer inspection activities required on a 3 yearly basis, and potentially for some of their assets that were nearing end of life, it avoids potentially an entire campaign needing to be performed before we reach that end of life. So for the cost of the study, broadly in line with a single DSV day, we've potentially saved that operator several times that amount of money over the remaining life cycle of their assets. Okay, so moving on, once we've performed our risk assessment and we've determined our inspection schedule, we then need to actually then inspect. And there's a variety of different techniques, technologies and approaches available for carrying out inspections and determining asset condition, and these will very much depend on what the asset is, where it's located, and the types of hazards that are being inspected for. I think it's worth reiterating that the type of hazard is important in terms of determining what inspection is suitable, what inspection is going to identify signs of that hazard. A former colleague of mine would quite often tell the story of an operator who he audited and found that he'd visually inspected his pig traps quite religiously every 6 months for the last 20 years, but he'd never actually performed any non-destructive examination of the trap. When my colleague informed him that fatigue failure of branch pipework and nozzles was quite common on pig traps, and that UT inspection was commonly performed, and in fact in this case formed part of the written scheme of examination for their pig traps. They were quite surprised by that and immediately went and carried out some NDT. What they found was that there were some very small cracks on their pig trap that they would never have ever identified through visual inspection, and could have potentially continued to grow to a point of failure under operation, where there could have potentially been personnel in the vicinity. So there's a lesson there that yeah, inspection isn't the be all and end all. You need to make sure that you're carrying out the right inspection, and then you actually do something useful with that inspection findings as well. So again, as I said there, the type of inspection is an important factor in identifying your hazards and ensuring you have the right information about your pipeline. Moving on to the next slide, the location of your assets will have quite a big impact on the techniques and tools that are available to you. Inline inspection is a kind of common, comprehensive option for carrying out inspection, and it will inspect for a number of different types of hazards, both internally and externally. It is still important to ensure that you're selecting the correct technology, because not all the technologies will identify the same types of hazards. So for instance, if you have a risk of cracking, you might not ever detect that with the traditional MFL. You might need to run a specific crack detection tool. And these are the kind of things that Penspen as a consultancy can support operators in ascertaining what tools and technology is available on the market, what's suitable for them, the types of vendors that are available on the market as well. The number of pipelines that might be determined as unpiggable has reduced over the last 10 or 20 years as inspection vendors have developed more novel and bespoke solutions, but there are still instances where ILI isn't possible, and then again there's then opportunity for alternative inspection methods to be adopted. So offshore, there's some challenges in terms of even conducting visual inspections. I think traditionally rope access teams were required to inspect things like risers and riser clamps. What we're finding is that increasingly drone surveys, or unmanned aerial vehicles as they're called, are being used, and that allows for more rapid visual inspection to be conducted. There's obviously a lot lower risk. Potentially it can be launched in worse weather conditions as well. And what that allows you to do is carry out a sort of visual inspection, and then if that inspection determines that there's a requirement for further inspection, that can be when you use your rope access team to either conduct some kind of non-destructive examination or carry out fabric maintenance or some other type of repair. We've seen the same already subsea, where divers have increasingly been phased out and ROV has increasingly been used. Again, the technology there is advancing, and we're moving towards autonomous underwater vehicles as well that don't require a tether to a vessel. And then there's other developments such as increasing the speed at which data can be collected to allow campaigns to be performed over a shorter period and save on vessel day rate. So we've moved from things like two-dimensional side scan sonar to three-dimensional multi-beam, and then hybrid technology such as multi-beam paired with things like photogrammetry or LiDAR, which allows for even more refined images to be captured while still performing sort of fast flybys. So there can be issues with that. I've seen sort of first-hand problems where sort of large amounts of data require a lot of processing. In one instance, I saw a pipeline actually be smoothed out of the XY data completely, and all the survey contractor could provide was a seabed profile, which wasn't very useful to a pipeline operator. So it is still important to ensure that you're choosing the right technology for the situation that you find yourself in. So, as I've said before, inspection on its own doesn't actually guarantee integrity. We do actually need to make sure that some kind of suitable assessment is performed of the data that's been gathered from inspection or monitoring activities. So there's a variety of hazards that can be inspected for, things like metal loss, whether that's corrosion or other means of metal loss, fatigue and fracture, buckling, denting from some kind of third-party interaction, and then subsea spanning as well. And the type of inspection and the type of data that you can actually recover from those inspections will inform the types of assessments that you can perform and how much value you can derive from having performed them. PenSpen is the author and manages the PDAM JIP, which outlines best practice for pipeline defect assessment. So we can provide a number of consultancy services in terms of assessing defects that are found through inspection or other monitoring. And then in September, PenSpen then launched THEA, which is an online cloud-based integrity management solution, the aim of which is to help operators maximize the value of the data that they gather from operation and inspection. And also allowing for more rapid assessment of defects, and that will hopefully support more rapid decision making in the context of pipeline integrity. As I've mentioned a couple of times now, data management is a key element of integrity management, and THEA will hopefully help operators in managing their data and aligning their data so that they can maximize the value of the different data sets that they retain through operation and inspection. Another benefit really in terms of the improvement in the speed at which assessment can be performed is not only does it give you faster answers, but it also means that you can perform more complex assessments where they might have previously been cost prohibitive or time prohibitive. And what that means is the more complex and refined your assessment can be, the more refined an answer that you can output from that assessment and potentially avoid what would have been an unnecessary repair or what might have been an unnecessary inspection if in fact the condition of the asset is such that you can push out that inspection interval for another year or two. So I think, as I mentioned before, and as Annie mentioned at the start, this is just one in a series of insights. So there'll be future webinars that will go into a bit more detail about THEA in particular and defect assessment in general. So then, just to complete the loop, really, we've been moving around the integrity management loop from risk assessment and planning through actually executing our inspections, assessing the findings from those activities, and then implementing the findings from those assessments. The key thing, as I've said, is data and ensuring that data is passed around the loop, that it's captured, and that it informs your future decision making. To ensure that you fully understand the condition of your asset and that your risk assessment is a true reflection of the current condition of your pipeline. So then, just to summarise, so hopefully what I've made clear then is that the goal of integrity management is first and foremost to understand and control your risks. That means that risk assessment is fundamental to integrity management. A risk-based approach to integrity and a risk-based inspection is acceptable under the UK legislation and is also found in a lot of code guidance. By directly linking risk to the frequency or the periodicity of the integrity management activities that you can perform, you can ensure that those activities are optimized and that you're only performing the activities that you need to perform at the frequency that they should be performed to maintain your risk at a tolerable level. Again, I'm going to mention that inspection alone doesn't guarantee integrity. You need to make sure that the data that you're recording is reliable, accurate, and is useful, and that you then do something with that data, whether that's review it or conduct an assessment if you find that there are defects in your asset. And then the key thing then is to make sure that the findings from that inspection, from that assessment, is fed back in to your risk assessment through the integrity management loop so that it can inform your future risk assessment and future integrity needs.